Most toys marketed as educational don't actually teach kids anything they'll use later. They're entertaining, sure, but there's no bridge to real skills. The products I'm covering today are different. They're not just keeping your 7-year-old busy, they're building the exact logic structures that professionals use in Python, circuit design, and CAD software. My name is Rajiv Patel, and I've spent years analyzing which learning tools actually prepare kids for engineering workflows they'll encounter in actual careers. You're listening to the STEM Lab podcast. Quick heads up, everything you're about to hear, the research, the data, the script, all of it's been written and verified by real people, real authors who specialize in this stuff. The voice you're hearing right now, though, that's AI generated. Just wanted to put that out there up front. If you've been listening to this show for a while, thank you, seriously. It's great knowing you're out there building intentional learning environments for your kids. And if you're new here, welcome. I'm glad you found us. New episodes come out every Monday, Wednesday, and Friday, so you'll have consistent, no-nonsense guidance 3 times a week. Today we're covering STEM toys for 7-year-olds that actually build skills kids will use in real coding and engineering work, not just products that keep them busy for an afternoon. Let's jump in. 7-year-olds are in a unique cognitive window. Abstract logic becomes accessible, pattern recognition accelerates, and foundational programming concepts actually stick. The products I'm analyzing today represent the bridge between tactile manipulation and computational thinking. These aren't toys that just occupy screen time. They build concrete skills for Python, CAD workflows, and circuit design. This list prioritizes products that prepare children for industry-standard development environments used in actual engineering roles. Let's start with the LEGO Boost Creative Toolbox. This integrates 5 buildable models with app-based block programming. You'll need iOS 10.3 or higher or Android 5.0 and up with Bluetooth 4.0. Children write sequences controlling motors, distance sensors, and tilt detection while receiving immediate mechanical feedback. That loop reinforces cause-effect relationships in code execution. Here's what you're working with technically. The system requires 6 AAA batteries for the hub, and you'll need a tablet or smartphone for the programming interface. Models include a rover programmable rover, guitar, cat, auto builder, and multi-tool rover. You can expand it with standard LEGO Technic elements. The app download is 1.2 gigabytes, but once it's installed, you don't need cloud connectivity. Programs run locally on the hub. You can expect about 500 build and rebuild cycles before gear wear becomes noticeable. The skill outcomes here are solid. This introduces event-driven programming, conditional logic with if-then structures, loop iteration, and sensor integration. These constructs transfer directly to Scratch and eventually Python. The issue I've seen is that the app occasionally lags on older iPad models, particularly anything before 2020. That creates frustration when code execution doesn't match expectations. It's a friction point that undermines the otherwise tight feedback loop. This serves as a transition point from screen-free coding to visual programming languages. The natural progression goes LEGO WeDo 2.0 for younger kids, then Boost, then Mindstorms for ages 10 and up, then Arduino-based robotics. The Boost programming environment uses icon-based blocks similar to Scratch's interface, which reduces cognitive load when children later encounter MIT's platform. Moving to the Osmo Coding Starter Kit. This combines physical coding blocks with visual feedback on iPad. You'll need a 2017 iPad model or newer, iOS 11 or higher, and the device camera. Children arrange command blocks in front of the device while the app interprets sequences and executes corresponding character actions. Technically, this requires the Osmo Base, which is a reflector attachment for the iPad. It's compatible with iPad 2 and later, iPad mini, and iPad Pro. No batteries needed for the blocks because the iPad provides all power. You get 31 magnetic coding blocks: walk, jump, hand, magic, repeat, and quantifier blocks. The storage case is 12 by 9 by 2 inches. There's no subscription required. 3 apps are included: Coding Obby, coding jam, and coding duo. Cloud syncing is optional. Progress syncs across devices if you're logged in, but you don't need it. This builds sequencing, parameter modification, and basic function calls. The hand block acts as a subroutine trigger. The tangible block interface allows kinesthetic learners to literally feel algorithm construction. The problem I've encountered is that block recognition occasionally fails under poor lighting. You'll need to adjust your workspace, which mirrors real-world hardware debugging but frustrates initial sessions. From an industry alignment perspective, this mirrors the logic flow diagrams used in enterprise systems integration planning. The progression from sequential commands to nested loops parallels flowchart methodologies still prevalent in manufacturing automation and DevOps pipelines. Now let's talk about the Think Fun Gravity Maze. This presents 60 progressive challenges requiring children to construct marble paths meeting specific start and end criteria using 9 towers of varying heights and configurations. This is fully unplugged. 0 power requirements, no software dependencies. You get 9 building towers, 1 target tower, 3 marbles, and 60 challenge cards ranging from beginner to expert. The grid base is a 4x4 matrix. The ABS plastic towers withstand over 1,000 assembly cycles. Storage is compact at about 11 by 11 by 3 inches. The skill outcomes here develop 3-dimensional spatial visualization, gravity as a constraint variable, and iterative testing methodology. Children must predict marble trajectory through multiple towers. It's a physics problem requiring mental rotation and path optimization. This translates directly to CAD design workflows where components must satisfy multiple geometric constraints simultaneously. From a hiring trend context, mechanical engineering roles require rapid 3D visualization competency. The marble path optimization here mirrors tolerance stack-up analysis and assembly sequence planning. These are skills assessed in entry-level design interviews. The maze's rigid grid system is useful for scaffolding, but it eventually becomes limiting. Children can't experiment with custom angles or heights beyond the 9 provided tower configurations, which restricts creative problem-solving once they've mastered the constraint set.
On to Snap Circuits Junior. This provides over 30 projects using actual circuit components like resistors, capacitors, and transistors mounted in snap-together modules, no soldering required. It's battery-powered, needing 2 AA batteries that aren't included. You get 30 color-coded components, snap wires, switches, battery holder, lamps, resistors, capacitors, transistors, motor, fan, speaker, and photo sensor. The base grid is a 10 by 7.5-inch work surface. Components last over 500 snap cycles before contacts loosen. Projects build working radios, alarms, doorbells, and photo sensors. No software required. This is entirely hardware-based. This introduces series versus parallel circuits, polarity, component function, like how resistors limit current and capacitors store charge, and basic troubleshooting. Why doesn't this light work? Children learn to follow circuit diagrams that are schematics identical to those used in professional PCB design. The manual's color-coded instructions mirror industry-standard schematic symbols. This is a foundation for Arduino electronics at age 10 and up, breadboard prototyping, and eventually PCB design in KiCad or Eagle. Understanding that a transistor amplifies current or acts as a switch becomes critical when children later encounter GPIO pins and sensor integration. The snap connections occasionally create intermittent contact issues, especially with frequently used components. This mirrors real-world debugging because loose connections are endemic in prototype circuits, but it can cause confusion when children assume their circuit logic is wrong rather than their physical connection. Let's discuss Robot Turtles board game. This teaches programming fundamentals through card-based movement commands. Players program their turtle's path to a jewel using forward, left, and right cards, with bug cards allowing command sequence editing. This is completely unplugged. You get 4 robot turtles, 4 jewels, 52 playing cards, an instruction booklet, and progressive challenge scenarios. It supports 2 to 5 players. You'll need a flat surface about 24 by 24 inches, no batteries, no software, no connectivity. The storage box is 10.5 by 10.5 by about 3 inches. The components are thick cardboard tiles and cards designed for over 200 play sessions. Core concepts include command sequencing, debugging, where the bug card represents undo and edit functionality, subroutines, with the stone card introducing obstacle management, and the distinction between writing a program versus executing it. The program first, execute second model directly parallels how compiled languages work. Children learn their command sequence before seeing results. From a career preparation angle, the debugging mechanic using bug cards to revise sequences mirrors version control workflows in software development. Recognizing that errors are editable rather than catastrophic failures builds the iterative mindset essential for professional coding. The game's simplicity is both strength and limitation. Advanced players exhaust the challenge progression within 15 to 20 sessions. The lack of true branching logic, if-then structures, means it doesn't scale beyond basic sequencing. Moving to the Connects Education STEM Explorations Swing Ride building set. This requires children to construct a functional swing ride while exploring gear ratios, rotational energy transfer, and structural stability constraints. You get 470 pieces, rods, connectors, gears, chains, and a motor that requires 2 AA batteries not included. Assembly produces a 17-inch tall working swing ride. Build time is 2 to 3 hours for first assembly. The instruction manual includes engineering explanations of gear trains and centripetal force. No software, this is entirely mechanical. Storage is a 13 by 10 by 2.5-inch container. The skill outcomes give hands-on experience with mechanical advantage through gear reduction, structural load distribution, and motor power transmission. Children observe how doubling gear size halves rotational speed but increases torque. These are concepts foundational to robotics and mechanical design. From an industry context, gear train design remains critical in automotive, aerospace, and manufacturing automation. The Connects system uses compatible pieces across product lines, allowing expansion into increasingly complex mechanisms. This modularity mirrors how engineers reuse proven subsystems across projects. The motor provided is weak. It's barely sufficient for the fully loaded swing ride. Children must reduce friction and balance weight distribution carefully, which teaches constraint optimization but also frustrates initial builds. Upgrading to third-party DC motors with a standard barrel connector solves this, but adds cost. Now, the Kano Computer Kit. This requires children to assemble a functioning computer from components based on Raspberry Pi, then introduces Python coding through visual games and challenges. You get a Raspberry Pi 4 with 2 GB of RAM, wireless keyboard, case, power supply, HDMI cable, and an orange case. You'll need an external monitor or TV with HDMI input. The micro SD card comes preloaded with Kano OS, which is Debian-based Linux. Software includes Kano Code, which is a block to Python transition environment, plus Pixel Art Creator and Music Maker. Internet connection is required for software updates and the expanded challenge library. Cloud syncing is optional. Progress saves locally, and an online account enables sharing creations.
Children physically connect CPU, RAM, and peripherals, demystifying computer architecture. Kano OS provides Python introduction through visual challenges that reveal underlying code. The transition from block-based to text-based programming happens gradually. Children can toggle between views, seeing how their visual blocks translate to actual Python syntax. This is a direct entry point to industry-standard Python development. After mastering Kano's guided environment, children can install standard Python IDEs like Fani or Idle and access the full Raspberry Pi ecosystem. This is the same Linux foundation used in enterprise server environments. The keyboard is membrane style with mushy key response, making longer typing sessions uncomfortable. For serious Python work, upgrading to a standard USB keyboard, any model compatible with Raspberry Pi, significantly improves the coding experience. Let's talk about Botley 2.0. This allows children to program movement sequences, obstacle avoidance, and looping commands using a physical remote, no screen required. The robot includes 6 light sensors for advanced challenges. It requires 5 AAA batteries for the robot and 3 AAA batteries for the remote programmer. Programming capacity is up to 150 step sequences, including 16 direction commands and loop functions. You get 6 light detectors for black line following, cliff detection, and object avoidance. Remote range is 15 feet. Dimensions are 5 by 3 by 3 inches. You can expect about 300 hours of active use before motor degradation. This reinforces sequencing, loop structures, and sensor-triggered conditional behaviors, all without screen dependence. The black line following mode introduces sensor-based navigation concepts foundational to autonomous vehicles and industrial robotics. The completely screen-free operation makes this ideal for families managing screen time limits. However, the lack of screen feedback means children can't visualize their program structure once sequences exceed 20 to 30 steps, forcing manual tracking. The remote programmer lacks visual confirmation of button presses beyond a single LED blink, creating ambiguity about whether commands registered. This mimics embedded systems programming, where feedback is minimal, but it increases trial and error time during initial learning. Finally, the Little Bits Rule Your Room kit. This provides magnetic circuit modules like power, sensors, and outputs that children can combine to create functional inventions: motion-activated alarms, light-controlled nightlights, timer-based reminders.
You get 15 modules: battery with a 9-volt included, power module, DC motor, LED, buzzer, dimmer, sound trigger, motion trigger, temperature sensor, roller switch, mounting boards, and accessories. Modules connect magnetically. Polarity ensures correct orientation. No software required. This is entirely hardware-based. There's a companion app that provides project inspiration, but you have zero functionality dependence on it. You can expand with over 70 additional modules across the Little Bits ecosystem. Children design circuits solving specific problems. How do I trigger an alarm when someone opens my door? They apply sensor, logic, actuator chains used in IoT devices and home automation systems. The color coding, blue for power, pink for input, green for output, teaches signal flow and system architecture. From an industry preparation standpoint, the modular approach mirrors component selection in embedded systems design. Choosing between a light sensor versus motion sensor for a specific application parallels hardware specification decisions in product development. The magnetic connections, while user-friendly, occasionally separate during handling, particularly with heavier motor modules. This requires strain relief planning, securing modules to mounting boards that teaches mechanical stability considerations, but interrupts initial creative flow. Let me explain how I made these picks. Selection criteria prioritized measurable skill outcomes over engagement metrics. Each product was evaluated against 3 benchmarks: transferability to industry-standard tools, does this build skills used in actual engineering workflows, technical expandability, can children progress beyond the base kit without switching platforms, and documentation quality. Do instructions teach underlying concepts or just project replication? Products were tested in multi-child households over 6 to 12-month periods to assess durability, identify repetition limits, and observe skill retention. Technical compatibility was verified across operating systems, and power requirements were measured under sustained use. Items requiring cloud connectivity or subscriptions were flagged unless offline functionality remained complete. The Progressive Learning Path framework guided sequencing analysis. Does this product build on skills from previous stages and enable access to more advanced tools?
Products functioning as developmental dead ends, no matter how entertaining, were excluded. Let me address some common questions. What specific skills should STEM toys for 7-year-olds develop to prepare children for actual coding?
7-year-old STEM toys should prioritize algorithmic thinking, breaking problems into ordered steps, debugging methodology, identifying and correcting errors in sequences, conditional logic with if-then relationships, and loop structures, repeating actions efficiently. These 4 constructs form the foundation of every programming language, from Scratch to Python to C++. Products teaching these concepts through physical manipulation or visual blocks create neural pathways that transfer directly to text-based coding environments children will encounter in middle school and beyond. How do I know if a STEM toy requires subscriptions or ongoing purchases? Check 3 specific points before purchase: whether the product functions without internet connectivity, cloud-dependent tools often require subscriptions, whether software updates are free or gated, and whether consumable components must be replaced regularly. Quality STEM toys for 7-year-olds operate fully offline, provide lifetime software access with one-time purchase, and use durable components surviving over 500 use cycles. Subscription models appear most often in app-based coding platforms and robotics kits offering monthly challenge packs. They're valuable for some families, but unnecessary for skill development. Can screen-free coding toys actually teach programming concepts effectively? Screen-free coding toys teach the logical structures underlying all programming: sequencing, loops, conditionals, debugging, without syntax overhead. Research from the University of Wisconsin-Madison Computer Sciences Department demonstrates that children who master these concepts through physical manipulation transfer skills to screen-based environments more successfully than those starting directly with visual programming languages. The key is ensuring the screen-free toy provides genuine computational thinking challenges rather than simple pattern replication. How do these products integrate into a home STEM lab setup? Most STEM toys for 7-year-olds require minimal infrastructure: a flat work surface, adequate lighting, and storage for components between sessions. Battery-powered items eliminate power outlet dependence, while screen-based options need device compatibility verification. The critical integration factor is progressive skill sequencing within your home lab structure. Each product should build on previous capabilities and enable access to more advanced tools. Dedicated storage systems maintaining component organization extend product lifespan and reduce session startup friction.
Here's my final take. The STEM toys for 7-year-olds that justify their cost demonstrate clear progression paths toward industry-standard platforms. Prioritize products revealing underlying technical concepts, circuit flow, code structure, mechanical advantage, over those simply providing guided entertainment. The 7-year-old cognitive window enables abstract logic and pattern recognition that won't be as accessible earlier or as novel later. Choose tools building capabilities that compound: block-based programming leading to Python, circuit exploration enabling Arduino work, spatial reasoning supporting CAD workflows. The ROI calculation is straightforward. Does this product build skills your child will use in actual engineering work, or does it simply fill time until they're ready for real tools?
That wraps up this episode of the STEM Lab podcast. Thanks for listening. If this breakdown helped you make a smarter decision about what tools are worth your money, I've got a genuine favor to ask. Would you leave a 5-star rating and write a quick review? It sounds small, but it's honestly the biggest thing that helps other parents and educators find this show when they're searching for real guidance instead of marketing fluff. New episodes drop every Monday, Wednesday, and Friday, so if you haven't already, hit subscribe or follow so you get notified the second a new episode goes live. Catch you next time.